Max suggested I might do an overview of the data analysis that is involved in observationally characterizing ring downs, and I'm happy to do so. If you want, these slides are here. Now's the time for a cell phone picture. And much of the material comes from this paper that Max and I wrote late last year. And so the goal of this talk, which I'm going to try to keep short, so we can get a little bit back on schedule and get out to lunch, is to kind of work through at least the conceptual picture of getting from here. This is LIGO data. It happens to be surrounding the very first detection, GW 150914. If I don't know if people recognize the GPS digits, I don't, but maybe some folks have. Max probably does. Yeah. So this is, Hanford and Livingston data that looks like crap. How do we get from that to something that looks like this? Hey, that's a ring down. I see damped sinusoids. Maybe I see more than one damped sinusoid. What's involved in that process? What are the conceptual issues? And then at the very end, I'm going to talk about what some of the sort of current work extensions, interesting directions to take this are. Okay, so the first thing to notice about this plot is that there are characteristic timescales in the LIGO noise, right? This plot is entirely noise. If I pasted the actual 150914 signal in here, I don't know if you can see, that's 10 to the minus 18. The 150914 signal peaked at a strain amplitude of 10 to the minus 21-ish. So it's like a pixel. In fact, all of this plot is noise, and you can see that there are characteristic timescales. There's this sort of, look at this beat note, okay, in the LIGO noise. And step one of doing data analysis is to write down a likelihood function. The likelihood function characterizes the noise in LIGO. So that's the first thing that I'd like to talk about, okay? So this is a simpler example, which comes from the paper with Max. Here's some 30 seconds of synthetic data that are meant to evoke, but not really in any way be terribly representative of the LIGO noise stream. And they're generated from a Gaussian distribution that has variances that depend on frequency, right? That's what colored noise means. It means the variance of my Gaussian is a function of frequency. And the power spectral density is the quantity that describes that. Okay, so if I take any finite width here, variances add, right? Powers add. When you're talking about noise, the linear term is always 0. The noise always averages to 0, or if it doesn't, then you have a bias and the experimenters go fiddle and knob and they make it go away because they're excellent physicists. So the first non-zero moment is the second moment, the variance, and that adds. So what this function tells you is if you pick some bandwidth over which you want to observe, okay, so I have my eyes, they have a certain filter. I have my ears, they're sensitive from like, a bit below 10 hertz up to 20 kilohertz or whatever, right? I have some physical thing that has some bandwidth. If I add all this up, I integrate it across that bandwidth, that is the variance, right? The second moment of the signal that I get. Alternately, if I have, a really high fidelity filter, a little tiny thing, right? I get a much smaller variance because I capture a lot less of the noise power. And in the limit that the size of the filter gets infinitesimally small, you get this function. Okay. The awesomest named theorem in all of physics is the Wiener-Kinshine theorem. And that tells you that if I have a power spectral density for some time series like this, if I take the Fourier transform of the power spectral density, okay, this thing is already working in frequency space. So when I actually compute it, I've taken the Fourier transform of my time series and done some averaging. If I take the Fourier transform of this thing, I get the autocovariance of the noise. What this is a time domain analog. It asks if I take some point in the time series of strain, and I take some point that is delayed by 1 second, 2 seconds. Okay, so I take this sliding pair of points 1 second apart, and I average them over the entire time series. What is the variance of that? That's what this function is. Okay, so it's the power as a function of lag. At 0 lag, this is the variance, right? Just the usual formula for, sum of the squares of x minus the mean. And at different lags, you can see that in the characteristic time scales, right? If you wait for 1/10 of a second, the noise is actually anti-correlated. And then if you wait for 2/10 of a second, it's positively correlated again. A sinusoidal term in this corresponds to a spike in this, right? They're Fourier transform pairs. Okay, so these are just equivalent ways of looking at the noise in LIGO. And at the raw level, if I want to work on the time series, I can use this to construct a covariance matrix for a multivariate Gaussian. So I'm going to see if I can fling up these chalkboards. So the autocovariance is traditionally written like that. And it's the average value of a product of the time series at some time and some time lagged by tau. Okay. So this is telling you what the expected value of this product is. If I now think about what I have in real life, right? I don't have continuous functions, I have samples, right? These are points on a plot. The discrete analog is just that, right? I take the average over the whole time series of pairs of points that are separated by some lag. Okay. So now if I'm willing to assume that my noise has a Gaussian distribution, its probability distribution is Gaussian, then I can immediately write down a covariance matrix where sigma ij is equal to the covariance at the lag between I and j. Let me explain what that picture is, why that works. People are nodding their heads. Maybe everybody's like, yes, totally makes sense. But okay, so what's happening here is the covariance matrix, right, in a zero mean Gaussian setting, the covariance matrix should be equal to what is the expected value of these 2 points. But these 2 points are just lagged by this, right? Let's, without loss of generality, let's just assume that j is greater than I. Right? So this quantity is just telling you what the rows of the covariance matrix looks like. So now let me draw this out. Here's a covariance matrix. The diagonal term has 0 lag. That's just the variance. Then at lag 1, then at lag 2. Okay. And here, these 2 terms are lagged by 1. And so on. Okay? Does that make sense? It has this nice cyclic structure. Okay? Now, right, so I just shift all these to the right, and I imagine bringing entries in from the front. Now, Max just narrowed his eyes at me because it's not always the case that this is truly cyclic. Okay? If I take some finite stretch of LIGO data, right? That looks like, I guess you guys can see on the sides. I can't see on the sides, but you can. That looks like that. The data is not cyclic, right? The correlations, what cyclic would mean is that as you go far enough, along, it repeats itself. That's not periodic. No way. Can't do it. However, if I have an infinite stream of LIGO data, the looping happens at infinity. So, who cares? All right. So an infinite stream of LIGO data we could treat as cyclic. And we could imagine this matrix goes on and on and on and on and on and on forever. And really what we're doing, somewhere way over here, it gets row 2, let's do this. Row 3, row 2, row 1, right? It counts down to 0. And then we pull the stuff back in from infinity and bring it around. If I had this circular covariance matrix, then I could diagonalize it with the Fourier transform. That's the situation we normally live in when we're doing LIGO data analysis. We take a long stretch of data. It has a little tiny waveform in it that we're interested in. We take more data off the ends, and we just taper those ends to 0. And we say, look, that's circular, right? It's 0 at the start and it's 0 at the end. It wraps around nicely. And we work in the Fourier domain. Yeah.
Okay. I just want to point out, you've also assumed that the data is wide-sense stationary by having the diagonals be.
That's right. I should have mentioned that right from the start. That's right. Assuming it's stationary is literally assuming that this only depends on the distance between the 2 points, not their position. In normal LIGO data analysis, where we have a complete, in spiral merger ring down template in here, it's a fine thing to take extra data on the sides, taper it to 0 to make it circular, and work in the frequency domain. In ring down analysis, that's deadly, right? We just heard you want to start at some point in time where you think the ring down is really a ring down. Now we're going to have a lot of discussions about that, I'm sure, in future days. Pick your favorite point. Wherever you start, you can't very well taper that to 0. That's the signal. If you include data from before that, though, it's contaminated by the merger and the in spiral. So what are we to do? Well, for ring down data analysis, it's fine. We'll just work in the time domain. Right? We don't have this circular property, but we still have a covariance matrix, right? I can still, take some subset of this full circular matrix, and I can just treat my data as a multivariate Gaussian. So the log likelihood for a multivariate Gaussian is you just take the noise term, you sandwich an inverse covariance matrix in between it, and multiply by half. That's the log likelihood. Okay. That's the way, with some extensions that I'll talk about when I get to the end, that's the way that all ring down analyses that are purely ring down treat their data. Okay. And I'm looking up at Finch and Moore because that's one of the extensions that's going to come at the end. All right. I will say that this is not something, even in the data analysis community, that has universally been appreciated until relatively recently. The first analysis that we did in LIGO did not work in the time domain. And for that reason, thankfully, was exceptionally low signal to noise ratio so that it was not dominated by bias. Okay. Any questions? Yeah.
What analysis specifically are you referring to there?
The original 150914 ring down analysis from the LBC, of which I was a co-author.
Which was done in the...
It was done in the frequency domain.
Yeah, exactly. Yeah. Okay.
Yeah. That's right. It was done in a frequency domain with a waveform template that was 0, 0, 0, 0, 0 ring down. Yeah. Okay. So now we had 2 talks, an hour and a half plus this morning, about what ring downs look like, right? They look like this sum over modes. P there is the number that controls whether it's a prograde or retrograde mode. There's an angular pair of quantum numbers L and M. There's a radial, not quite, but whatever, radial quantum number N. There are complex frequencies. There's, spheroidal or spherical harmonics. ultimately, when this goes into a detector, none of that is available to us. Sadly, we do not have a cosmic network of gravitational wave detectors that can explore the celestial sphere of the merger. We sit at one place. So ultimately, all the modes, the constant M, different L modes mixed together. There's various, amplitude factors from the propagation out front. There's, amplitude that comes from the total mass, et cetera. All of that ultimately just gives you an H plus and an H cross at well-defined frequencies. And you can decompose, so this is the complex strain, so the real part is plus and the imaginary part is minus cross. You can decompose that in a number of ways, but it's at least an entertaining exercise to decompose it just like electromagnetic radiation into an overall amplitude, an ellipticity, which refers to the ratio. This is now an H plus H cross space, right? The two quadratures, the plus and cross quadrature, go around in an elliptical pattern. And epsilon is the ellipticity of that, right? Epsilon equals 1 gives you circularly polarized. Epsilon equals 0 gives you linearly polarized at some angle. Okay, there's a phase to the two. In this picture, these are sort of counter-rotating modes. There's a phase to each one. The frequencies are the same as those frequencies. And yeah, that's all I wanted to say. So what we ultimately detect is just two independent damped sinusoids for each mode. A plus sinusoid and a cross sinusoid, if you like to think of it that way. A left sinusoid and a right sinusoid, if you like that polarization. An amplitude sinusoid with some ellipticity, however you want to do it. There's just those 2 degrees of freedom for each frequency.
It's worth clarifying when you said counter-rotating, we don't mean prograde versus retrograde modes. You're talking about right-handed versus left-handed polarized in this picture.
One goes this way and one goes that way.
Maybe also worth pointing out that we may not even get that much if we only have 2 co-aligned detectors.
That's right.
So
if your
we may get even less.
You really only measure one number, which is how it projects on your detector. That's an unfortunate feature of the way LIGO Hanford and LIGO Livingston are arranged. Okay, so the part, all of these bits, amplitudes, polarization, amplitudes, ellipticity, even phases, relative phases of the different modes, the different polarization modes, not linear modes. All of those things are hard. That's what we discussed this morning. In order to actually understand what those are, you have to know that the system came from a pair of quasi-circular, orbiting black holes that inspiraled and excited the modes in some way. That's too hard. So for the purposes of data analysis, typically to make a clean measurement, though we will discuss this in depth later in the workshop, we leave all of these things free. They're just nuisance parameters. Each mode has an amplitude, there's a polarization angle, there's a phase. All of those things, we just fit for them in the data, let them be whatever they need to be. The principal thing we're interested in as a test of GR is the frequencies and the damping rates of the modes. So here I'm showing these are all the 2, 2, L equals 2, M equals 2, so expected to be sort of the dominant angular emission pattern. Overtone frequencies and damping rates. If you scale by the mass, or equivalently the time associated to the total mass of the Kerr remnant, there's only one parameter here, it's the spin, right? So if the mass is just a dimension. And so you can see here that at low spin, the overtone has, the fundamental and the first overtone, the second overtone, the third overtone have slightly different frequencies, but really not radically different, right? The overtone frequencies are pretty bunched up. Like this is a maybe 10% difference at best between the fundamental and the first overtone. as you increase the spin, they all asymptote to infinite frequency and they get scrunched up. In this, the distinction between the overtones is in their damping times, right? That's really what the n is counting. So it is like a radial quantum number, but the modes are not like the hydrogen atom modes, where n equals 0 and n equals 1 have wildly different frequencies. That's not what happens. Okay, so here, the fundamental has the longest damping time. The first overtone has about half, or maybe a little bit less, that damping time, and so on and so on and so on. And the damping times are relatively independent of spin and have this sort of almost logarithmic like, or maybe log squared, I don't remember the precise formula, but you know, a relatively slow and gentle divergence to infinity as the spin goes to 1. So these are the things that we're trying to extract. And effectively, well, at least the simplest picture of a test of GR, right, from this analysis is to measure some frequencies and measure some damping rates and ask if I can draw a vertical line anywhere on this plot at one consistent value of the spin to match all the damping rates and all the frequencies that I measured. Right, that's the like 0th order black hole spectroscopy test of GR that we might want to do. I will say these are all modes, but the shitty modes. Okay, this thing is not ringing like a bell, it's thumping like a table. Right, this is the quality factor, number of cycles to decay to 1/e in energy. And for the fundamental at 0 spin, the quality factor is like 2.1. And it gets worse with overtones, right? About the same frequency, but they decay much faster. So these are really soft, ooshy, dying modes, right? If you make the spin really high, again, this sort of diverges quasi-logarithmically again because of what's happening to the damping rates. If you make the spin really high, you can get long-lived modes. But those, you know, that's not an astrophysical situation. Okay. So how do we do this? Well, I told you how we model the noise. I told you how we model the signal. We take a data stream, we propose a signal, subtract it, assert that what is left is noise, and calculate the probability of that. And then you shove that in your favorite stochastic sampler that does MCMC or nested sampling or whatever your favorite approach is. And you sample and sample and sample and sample until you can build up a posterior distribution over waveforms. So this is a mock data example, but it's meant to evoke 150914, right? Up here is the raw data. The blue line is the signal that we put in, right? And then the band around the blue line is our uncertainty about what the signal could have been. That is to say, it's a sum of all the modes that we fit. But down here, you can see the actual mode content, right? We have a fundamental, which is long-lived. We have an overtone, which is short-lived, right? It barely lives for 2 cycles. And we have our uncertainty about each one. If you prefer to think spectrally, we have measured a frequency and a damping rate for these 2 modes. And here's something I want to touch on a little bit. So in the past, I think people have had an intuition in their heads thinking about Fourier series. If I have 2 tones at 2 different frequencies, when am I able to distinguish them? Well, it depends on the difference between the 2 frequencies, right? And that's all there is. If I just have sinusoids, not damped sinusoids, there's just frequencies. So there has been a thread, at least in the ring-down literature, that argues we will need exceptionally high signal-to-noise ratios to distinguish ring-down modes, because it looks at the frequencies of these 2 modes, which are different by 5%, and says to distinguish either of these modes from each other, I'm going to have to measure their frequencies to 5%. Happily, ring-down modes are not sinusoidal. They're damped sinusoids. So you can see from this picture, basically right away, that you need more than one mode. Because if you go to late times, all that's left is the fundamental. If I go backward in time, it should grow exponentially, which would predict an amplitude here. The actual data, however, have an amplitude significantly smaller. That was Chris's point from this morning. And you can achieve that by adding in with opposite phase the overtone at almost the same frequency, right? All these signals are coming in at basically the same frequency. The overtone kills the amplitude for the first 2 cycles and then dies. Right? So I don't need to be able to tell the frequencies of these tones apart as long as they have wildly different damping rates. And that's what you see here, is that you can tell there's 2 modes in this because we measure the frequency and damping rate of one and the frequency and damping rate of another, and they're they're distinct from each other. Okay, so this is, I don't know if you noticed, but on this slide heading, I put detection in quotes. Detection means many different things to many different people, and even means different things to the same person at different times. But one way to argue that we might have detected these modes is to say, look, I have measured the frequency and damping rate of 2 different damped sinusoids here, and they're distinct. Right? I actually saw something. If I hadn't seen something in the data, I wouldn't have been able to do this. There's other senses of detection that we can talk about later in the workshop. There's an entire session focused on what does it mean to detect a mode. Yeah.
If I understand correctly, you think before whatever your peak size is, before peak, the ring down can fit, ring down can fit, basically because you have these 2 modes that have opposite amplitude.
Keys your seat mic, please.
Hi. So I'll say it again.
Yep.
What I mean to say is that if I understand correctly, before the peak, you can get a sinusoid, predicted sinusoid that's lower in its final value, simply because you have 2 modes that sort of try to cancel out and make sure that before T peak, you don't have another peak.
That's right. And you saw this, and that was Chris's question I thought was really aptly phrased this morning, which is this seems to be kind of a generic feature. You could in principle read it off the plot that Saul showed of the mode amplitudes. Each overtone gets a bigger and bigger and bigger amplitude at the peak strain.
Right.
It's not that the strain is huge. The strain is pretty gentle and well controlled there. What's happening is each new overtone comes in out of phase with the last. So they're fighting each other near the peak.
So is that a feature of the actual coefficients of how ring downs are excited, or is it a feature of how our data analysis pipeline is trying to make sure that it fits before the peak?
That is an excellent question.
We'll cover it in the next session.
Yeah. I do not know the answer to that question. It seems like a little bit too much of a cruel coincidence of nature if there's not some deeper physical principle at work, but I have no idea.
Can I ask? Oh, sorry. Can I ask a completely different question on this slide as well? So here it's very, very clear in your right-hand plot that you can separate these 2 in F and tau space.
Yep.
If you were to use a logarithmic axis, particularly on the tau y-axis, is it quite so clear then?
Yeah, these credible regions stay about, I mean, they distort and change shape. But yes, these are still pretty clearly separated. In fact, it's a historical accident and an unfortunate choice that when we write, we tend to use tau. I mean Max and I, who've done this a lot, and other people as well. Really, if we used gamma, the damping rate, these contours would be a lot more pleasingly circular, because then F plus I gamma over 2 pi is the complex frequency, and all components of frequency have similar sorts of uncertainties and behave the same. Colin?
The one thing though with it's true you can separate it in damping time, but when you're measuring the damping time, you're essentially measuring an amplitude effect, and measuring amplitude effect is always more difficult than measuring frequency because you're much more sensitive to the phase, and that's the difficulty here is for a given SNR to distinguish between 2 different damping times, you need sorry, let me reword that. To distinguish between 2 different damping times, you need much larger SNR than you would to distinguish between 2 different frequencies.
That's true, although it's not a pure amplitude.
It's not a, sorry, say that again?
So the phasing matters.
Yeah.
Right? It's an amplitude over time.
Yeah.
So we get better uncertainties in the damping rate than you might naively expect from just, at SNR 10, we should be 10% uncertain about the amplitude of the signal. we get a little bit better uncertainties because, the amplitude has to decay in a certain way, and so it gets mixed into the phase, right? They're not pure tones. But indeed, it's often the case, at least for the fundamental, that the decay rate is poorly measured.
Yeah.
And that's exactly the SNR that you're talking about. For the overtone, I don't know the relative accuracy. Maybe if we made it on a log plot, they'd both look long and skinny, but certainly in the overtone, the damping rate is actually better measured because we only get like one cycle. Who knows what, as long as there's a peak here to reduce the overall amplitude of that, and there's a trough there to reduce the overall amplitude of that a little bit, we're fine. So the frequency can change quite a bit. The damping rate is pretty well constrained because we don't see anything happening in this third cycle. Right. The whole rest, from the third cycle on, is just pure exponential decay of a single mode.
It's also worth distinguishing between absolute
Yeah.
precision and relative, because you might not be able to constrain the fractional change in the damping rate that well, even though you separated absolutely pretty well in this plot.
Yeah, no, I mean, this is,
Sorry, I have just one question. Maybe you already this, but did you do this analysis looking for the two modes at the same time?
Yes. This analysis and pretty much everything I'm going to show is looking for multiple modes at the same time. There's no subtract off the fundamental and then fit the overtone from the residuals or something like that. Though often conceptually, that's the easiest way to picture what's going on. You latch onto the fundamental and then you kind of take that off, and what's left, in fact, it is all put in the soup, stirred in an MCMC, and out comes the result.
And so also the amplitude and the phase are free for the two modes.
Correct.
Everything is free. The frequency, decay time, amplitude, and phase.
In this case, yes. In other cases, sometimes we will fix the frequency and damping rates to a GR value coming from a common mass and spin through the Kerr ring-down relations. In all cases, the amplitude, the ellipticity, the phase, and the polarization angle are independent per mode. Does that help?
Yeah.
Sweet. Okay.
Well,
yeah, Max says there's other online questions. Yeah.
Yes, sir. Can I go first?
Yeah.
I was going to ask what the SNR in the ring down is for this case.
I don't remember the precise numbers, but it's 150914 light.
Okay.
This example, it was a little louder, maybe.
Like 14 or?
No, that's 150914. It's like, I think this is closer to 20 here.
Okay. Hang on, other online questions?
Yes. So Will, just to clarify, this is not real data, right? So you didn't.
That's right. This is fake.
You don't have this plot for the real GW5914.
I don't have it in my presentation. I can flash it up after if you want.
Okay.
I don't have the one on the right. I've got these two on the left handy.
Yeah. No, I was
laptop.
referring.
But yeah, this is fake data. It's meant to be evocative, but it's not real.
And it's
okay,
not
good for clarifying.
For actual data, we don't let the frequencies be totally free. So that's the distinction.
Yes. Yeah, in this case, this is just fitting damped sinusoids. So these frequencies and damping rates are totally free, which is not a thing we would typically do in, real data.
But it was not zero noise. This was with Gaussian.
Yeah,
noise
no, you can see there's
okay, good.
Noise.
No, I was just asking if the one on the right corresponds to the one on the left.
Yeah, the one on the right corresponds to the one on the left.
And so yeah, because when we try to do this on real data, what was happening often is that there is the problem of label of the modes, so you have to also take care of that, and which kind of slightly complicates this because sometimes the two modes so the sampler can assign one labeled mode to one physical mode and vice versa. So I think that would look worse on the real data also.
In this case, I believe we imposed that the zero, like all the, what Gregor was talking about is label switching. If they're just damped sinusoids, if you change 0 for one, swap all the frequencies and the amplitudes between the two terms and you get the same waveform out. but it's a different place in parameter space. So your sampler will struggle. So we broke that by enforcing that the damping time for the fundamental is longer than for the overtone. And then there's just questions of sort of initialization, like sometimes you fire up a sampler and the first thing it latches onto is this quickly damped mode, but it calls that the fundamental. And then the overtone has to live down here somewhere and it goes off the rails in its initialization and you just kill the run and try again. And eventually you can sort of, work your way around to something you believe is converged and doesn't have this initialization.
But it's worth adding that that's not an issue about actual data versus synthetic data.
Yeah, no, that'll happen here too. Yeah, label switching is a problem in all of these.
No, yeah, sorry. What I meant is that with the real noise, that gets worse usually than at least in my experience with the real noise, it's more complicated than Gaussian noise, but of course it will happen for everything.
Yeah, that's right. Colin?
Yeah, sorry, I just wanted to ask, so to prevent the label switching, you said you required that the damping time of the overtone be longer. Did you have to put any sort of window over around that, like that the damping time of the overtone had to be like 10% larger than the fundamental, or just simply
not in this
greater
beautiful circumstance, because they're generally so far apart that they never kind of bang up against each other.
And that was just because the SNR was high enough.
Yeah, if you're fitting, like if you're fitting pure noise, you have no actual ring downs in it, then they slam up against each other a lot, and then things get kind of ugly. And you need to put some kind of window in there.
If you had two modes that are closer in the vertical axis, then the two contours would sort of like join like two amoebas or something. But we enforce that ordering, so they will not overlap in this case. Roberto.
Yeah.
There.
Hello.
Hello.
Can you hear me?
Yep.
Yeah. So my question is still on the plot on the right. So this is not zero noise, right? This is one realization of the Gaussian noise.
Yep.
But what happens if you have different realization? Because like the different realization should change, I think, the center of these two Gaussian blobs. So it might happen, and it's probably likely to happen, that the two distribution on time will overlap on each other, right?
Yes, that can happen. You can kind of get a sense of it. The crosses here are truth. And if you regenerate random noise, run again, these curves shift around. From the offset between the peak of the curve and the cross, you can have a sense of how much they tend to shift around. So it's not impossible to get overlapping tails here in the marginal. That happens, whatever, 5-10% of the time. I don't know what criterion you want to impose for that. But I mean, this is the, Max, is this 10, 50, and 90? Yeah. So this is the 10th percentile, the 50th percentile, and the 90th percentile. So these are separated at the 90th percentile. So it's not super common that there's overlap in these contours, but it happens 5-10% of the time. And I will say, this is generically true of any sampling algorithm, but a very, very stringent test of a ring down code is to draw ring down mode parameters from the prior of the code, draw noise from the likelihood function, put them together, fit them repeatedly, and in that circumstance, it should be the case that the true value is uniformly distributed throughout the inferred values. So you can make a thing that we call a PP plot. Maybe I can show you here, that just shows, it's above, the statisticians would call it the coverage, but it's what fraction of the time, I don't know, Max, this is getting awful early. Yeah, there it is. There's no question about that. So this is showing for the various parameters, this is still two mode fits. This is the fraction of time, I don't remember whether this is the quantile of truth or the fraction of time that the quantile of truth is less than. But anyway, 20% of the time, you should find the true value further out than the 80th percentile. And 50% of the time, you should find the true value further out than the median. And 90% of the time, you should find the true value further out than the 10th percentile, right? The coverage is, and this is just showing, you know, that our sampler works pretty well. And this is a standard thing we do in LIGO, and I think other codes as well test themselves this way. But it's quite rigorous because this can fail either because you don't understand your model, so you didn't actually generate the noise you thought you generated. It can fail because your sampler is practically insufficient. So the, you know, statistical distribution you wrote down is correct, but you can't sample from it well. It can fail because your post-processing of calculating all these, you know, this is like a complete end-to-end test of your theory. It says nothing about how well things function in real data, but it at least tells you that your code has a hope of working properly. Are there more?
So, well, one more question.
Sure.
In the right plot, since you're kind of sorting the damping rates by their damping rates, does the prior itself somehow separate the two modes?
So before the sorting, the prior does not.
Okay.
After the sorting, what you'd get is the classic thing where, you know, if I have, right here, can people see the blackboard? I don't even know if people on Zoom. So if I just have two parameters here, actually, Chris has written a nice paper about this too, which lays out all the various, what was that? Yeah, thank you, Ricardo. Wrote a really nice paper about this that lays out all the possibilities. But if I just have two parameters and I give them a uniform prior, and then I impose the constraint that x1 is greater than or equal to x2, what I get for their individual distributions is, their marginals, is a triangle. Right, I get. So x2, the marginal x2 is big for small values because that's where most of the phase space is and decays linearly. And the marginal x1 is the opposite. It's 0 for small values because there's no space for x1 when x2 is small. Or sorry, the other way. I have this the other way around. Yeah. Yeah. Sorry. There we go. And this one should go. No, I think I had it. Anyway, VJ, sorry, you see what I'm trying to describe here. Yeah, there's no constraint. There's no difference between the priors on the times until we impose the cut. And then each one gets a marginal that is a linear function, you know. Okay. So you can also talk about detecting modes by just looking at the amplitudes. Here, things are a little bit more delicate, basically practically. So if you think back to this equation, what actually turns up in the data is a linear function of the plus amplitude and the cross amplitude. And in fact, is a linear function of the quadratures, the cosine part of the plus and the sine part of the plus. So there's a 4-dimensional amplitude space, which is either plus cosine, plus sine, cross cosine, cross sine, those 4 numbers. And those are nice because they show up linearly in the detector. Or amplitude, ellipticity, phase. Where did I lost a number? And angle. Yeah, 2 phases here, which corresponds to the polarization. Those don't show up linearly in the detector. And in particular, the transformation from the 4 quadratures to this involves a Jacobian that gives you an a cubed term near the origin. So if your prior is well behaved, I'll leave that. If your prior is well behaved in the quadrature space, you will have a nice time sampling because those are linear parameters. Linear parameters are easy to sample over. But you will intrinsically, just geometrically, because I'm going from a 4-dimensional space to a radial coordinate in that 4-dimensional space, be placing a prior on the amplitude that goes to 0 at the origin. That is, you'll be saying, I know I've got some of this mode, which may not be what you want to do if you want to test whether you have detected the mode. Contrary-wise, if you impose a flat prior, so you say, I don't like that, right? I want to explore the small mode amplitude region. So if you do this,
Will, could I ask you to pull the board up a little bit? Because the contrast is blown out because of the, oh.
Is that better? Hang on.
The contrast is just always going to be blown out. Oh, there we go. Thank you.
Better? Sweet. So if you want to put a flat prior on the amplitudes, then you have this divergence at the origin in the quadratures. Those are the things that actually turn up in the waveform. So your sampling is generally much harder here because your sampler still has to explore this 4-dimensional space, and either it has to account for all the coordinate wrappings of angles and so on, or if you do it in quadrature space, it has to climb up this integrably singular curve near the origin. So generically, it's not fun to try to show whether you've detected a mode in amplitudes or not, because that's a difficult coordinate system in which to work. Nonetheless, it's interesting. And so, for example, in this circumstance, if we ask, are there 0, 1, or 2 modes, what we see for the amplitude of the 0, 1, and 2 modes, when there's 0, we get the amplitude totally wrong because we're trying to fit everything with the fundamental, and it tries to make some compromise. When there's 2 modes, we get the amplitude 1 and amplitude 2 pretty well right. When there's 3 modes, we actually have trouble telling whether there is just a first overtone and no second overtone, or just a second overtone and no first overtone. You get this bridging structure here. And it's because you're a little bit uncertain of what's happening at early times. There's only a couple cycles there anyway. And either of the overtones can act on that first peak to shrink how it appears in the data, right? Remember, we were here. The height of that peak is lower than this. And you can achieve that either with the first overtone or with the second overtone, which dies even faster. It only does this 1 cycle. But you still get sort of the behavior of that first peak right. You get the second peak a little wrong, but at this SNR, you can't tell the difference. Yeah.
But would that mean that what this cannot do is this cannot, let's say, separate the posterior for the first overtone and second overtone? Because even if, let's say,
Keys your seat mic, please.
Maybe talk into your. Yeah, that's right.
If you were to, let's say, add second overtone as well, which also has, let's say, even smaller decay times.
Say it has decay times that are sort of down here.
So what you're saying is that we won't be able to separate these two.
That's right.
Like I said, if instead of talking about, let's say, tau, which is the decay time, we talk about the damping rate, gamma, what you call, right? In that case, there's a big difference, right? It goes like overtone number n. So
yeah,
that is, you should be able to, let's say.
Well, the problem is that this SNR, here is a factor of 2 in gamma, right? A factor of 2 in tau is also a factor of 2 in gamma. So at this SNR, we're not even sensitive to a factor of 2 in gamma. So the n equals 3 versus n equals 2, they're like a 3/2 or something close to that. So that's why this is happening.
But in the plot you were showing, it wasn't parameterized in terms of mass and spin, right? You're just asking.
Yeah, no, this is still just sinusoids.
It doesn't know that this second overtone. It just knows that it has a faster damping rate. It doesn't know how much faster.
Yeah.
Right. So you're asking, can I fit it with just two modes or with three? And they are ordered, but there's no pair here. It doesn't know anything about it.
No, we're leaving them totally free. So this is just, if I have two modes, which is just two damp sinusoids at arbitrary frequencies and decay times, I can fit the data. If I have three modes, I can still fit the data. And in fact, I can do it by picking a subset of the three modes, right? This is like actually two modes are in existence, and this is actually two modes are in existence, or some combination of the two. I can't really tell the truth. But you see this even when you put in Kerr in real data for the same reason that you just, pointed out. Yeah.
I was wondering if you've ever thought about including this destructive phase observation into the prior, and whether that would help recover the overtone amplitudes.
We've talked about it over pad thai. It seems like it would be a great idea. Generically, it's not totally clear. The limit of that is, well, just use a waveform. And so where on the spectrum from, I have damp sinusoids and I know nothing about their amplitudes and phases, to here is GR, what is the right point to live on that spectrum is not totally clear. One thing you could imagine doing is taking the SXS catalog or some other large catalog of mergers, calculating the amplitudes and phases in that 4D space, and then fitting it with some simplified model that just tries to capture correlations, like a Gaussian or something, and then using that as a prior. But
can I make a comment on that?
Yeah, please.
So the further you go down that route of trying to incorporate more and more information, at some point you just end up back doing a full in-spiral merger ring down analysis again. Like if you incorporate all the information from numerical relativity, you're just back to where you start, and you're no longer doing a ring down analysis, which is not a bad thing to do, of course, but it's sort of throwing the baby out with the bathwater.
Well, I mean,
you can isolate what you care about. This is the EOB ring down test, where they only vary frequency and damping time because that maps to mass and spin, and you don't care about amplitudes and phases, right? So just isolate what you're.
But it's no longer a pure. It's no longer a ring down test. It's now something else.
True, it assumes that the initial conditions translate to the final amplitude and phase as GR, and you just vary frequencies and damping times. Yeah.
Which may or may not be right, but it's definitely interesting.
Yeah.
And it also assumed that whatever came before the peak was actually well described by GR, because you're feeding all the information into your prediction. So if you want to be consistent, one could argue that you should ignore what came before, because also the spiral would be different from GR, not only the ring down.
Yeah. In fact, I will expound on that. That's an excellent point. That one of the strengths of doing this analysis in the time domain is if you were worried about that sort of thing, you can just paint out the middle part where some nonlinear space-time dynamics are going on and think only about the early in-spiral where there must be a PN series of some form, and the ring down where there must be damp sinusoids, and just forget all that stuff in the middle. Now, we don't have the SNR to make that very practical currently, but one day we might, and that might be an interesting approach to testing GR. Okay, I'm going to take two more questions, and then we're way over time, and I'm just going to flash some extension slides. So Colin's had his hand up for a while.
Sorry, just going back to that phase question. I mean, you don't have to. It sounds like the two extremes have been presented: either uniform prior on the phase, or fix them to exactly be out of phase. But you could do something like use a Gaussian prior on, So, and if the evidence supports it, then.
Yeah, no, I think that would be a very interesting thing. We have an entire session later on your last sentence, which is if the evidence supports it. And I will say that I personally am not yet convinced that we should be looking for these different approaches and picking one based on the data. I would prefer to pick them based on, this works in numerical relativity. Now we'll translate it to data. But that is a discussion that we're going to spend a long time on, I hope, because I think it's a very interesting question. And yes,
session on parameterizing the ring downs, I think this could fit well into.
In fact, I'll just save all this stuff. This is like parameterizations. And I will just say, what I have described to you is the simplest, but by no means the only thing to do. For example, if you don't like to pick the sharp start time and work in the time domain, you can impute, it's a statistics word, I guess. It means infer the noise from before the start time. And if you do that, you're doing something very much like what Colin did. And that corresponds to just taking your residual and projecting it in such a way that it doesn't, whatever the residual is before the start time doesn't affect your likelihood. So this F matrix is sitting there and is doing that projection. And if you want to know how the linear algebra for that works out, read Colin's paper. You could alternately fill in or impute the waveform before the merger, and that's the Finch and Moore approach, which lets you work in the frequency domain. Now you have this nice smooth thing that goes for a long time. You can taper it to 0 over here and taper it to 0 over here and make everything circular. So you can work in Fourier space again, where things are periodic. And I think that's an exceptionally interesting approach because it, can actually learn about the waveform beforehand from multiple detectors. In this picture, and in the picture that I was showing, what's happening with the noise in each detector beforehand is just treated independently. There's no crosstalk communication between the detectors. But if you have a consistent waveform, then once you have worked out what the waveform is before the peak, now you can go back on a detector by detector level and you know better what the noise is before the peak. And because the LIGO noise has autocorrelation from time to time, knowing more about the noise before the peak tells you about the noise after the peak, which is the thing that's effing up your ring down. So, I think this has a lot of power ultimately, though it also has a potential for systematics and how you stitch these things on. And you have to always worry that you're doing that in a way that's, respectful to the GR test that you're trying to perform. Okay, whatever. Also, if you can do it for one, you can do it for multiple, and people have written about how to stack these things on top of each other, including Max Caterina and I wrote about how to stack, which is the way that we tend to do it in LIGO. But additionally, Gregorio has a paper on this, which also you should look at this paper by Maselli. The idea there is we don't know anything. We're just going to measure the deviation from GR in multiple ring downs. GR says that should always be 0. Let's just infer what the mean and scatter of the deviation is. And if they're ever non-zero, then we found it. Here, it's a little clever. It's saying, well, in any modified theory of gravity, the deviation should depend on the mass and the spin. Those are things that are probably still properties of modified black holes. And therefore, we can think about how the frequencies and damping rates deform as functions of the mass and spin. And we can learn the parameters of those functions. And if those functions are non-zero, then things are not GR. But all of this is just a way to, if you do it in one, you do a test of GR in one ring down, you just stack it together and get multiple tests. Yeah, and we will return to that tomorrow. Yeah. No? Okay. Sweet. Finally, returning to the original slide back here where I just chucked out this morning, right? That was the rest of the talks this morning. Yeah, forget all that junk. We just do damp sinusoids when we do data analysis. Maybe that's not quite true because, we can't go to different places on the celestial sphere of one black hole merger, but we might hope that we are isotropically distributed on the celestial spheres of all black hole mergers. That's a thing that is probably true and very interesting to test. Now this isn't GR, this is the cosmological principle, if you like. The statement that we are found isotropically on the spheres of all black hole mergers is really a statement about the statistical distribution of the amplitudes and phases of ring down modes in black hole mergers. And so you can sort of go back to this picture. We can't actually measure any of this junk in one black hole merger, but that it better be consistent over the population of black hole mergers with what you'd expect for being just randomly placed somewhere on the sphere. And that's like a test of cosmological isotropy. that one could imagine working out if you knew well enough what the distributions of amplitudes and phases that GR would predict is. Chris? Yeah.
So that's an interesting idea. Why would you want to do that specifically from the ring down, and why not just from the whole?
You should
signal?
just do it from everything. But ring
Yeah.
downs are clean, so
Yeah,
you know,
okay,
it's one
yeah.
more place where you could do it, even if you don't, you know.
Yeah.
Yeah, we're in a ring down workshop.
Fine.
Yeah, no, you should do this. And there, I mean, there have been a number of tests along that line with all the waveforms. I just mention it because people are, you know, very keen to try to, you know, I know there's a spin-weighted spheroidal harmonic in here somewhere. That's where the spin-weighted spheroidal harmonic comes in. Okay.
But GR predicts, yeah,
Yeah.
we're several steps from
Yeah.
that.